Hi, everybody in the room and you at home. My name is Joe Klein. I am a, hacker, and we're going to talk about this because people are getting confused about really what this means. I've got lots of certifications. I'm actually a fellow for the IPv6 Forum, have been for 6 years, and have been into the IPv6 community now for 16 years maybe, doing security research in this domain, helping write standards, designing products, designing defenses and attacks, just primarily looking at this from many different views. This presentation, oh yes, I'm also CTO of Disrupt6, which we create IPv6 specific products and services. Security researcher and a trainer. I have a new set of training coming up in February, which is a 4-day, I only know networking to, here's how to hack or to defend IPv6 only environments, which is pretty fun. It's only taken an additional year for me to write it because I had a lot of labs I wanted to write. And then there's my contact. If you want to add me to your Twitter stream, there's my Twitter. And by the way, so I spoke at Bogota on IPv6 Security a month ago, and I consider now my blue period, and they informed me that I was definitely a hacker. So with that, I like the 1960 version of hacker, okay? I explore the details of programmable systems and how to stretch their capabilities. Okay, and then this one's also good. IETF, standards body, you know, intimate understanding. That's kind of interesting. Of internal workings of systems, computers, networks. Okay, it wasn't until 1985 where that definition of hacker changed from somebody that would be considered an inventor to someone's considered a criminal. So I just want to mention that. I usually preface this particular talk on that. So, sorry, this is the high level stuff. Computing has driven the prices down. For every generation, we've actually brought on new protocols, new systems, new applications, new concepts. We have this growth curve that doesn't look like it's going to stop at least maybe 2030, 2040, based on at least current physics, current understanding, current other things. So this is going to continue for a while, which means if you're in the information security domain, woohoo, we're going to still have jobs. Okay. And yes, there are now more devices than there are people. Okay, how many devices do you have on you? Okay, I have 5. Okay, at my home, I have herds and herds of little things. Okay, maybe I'm abnormal. You know, maybe I should be worrying about, you know, Arnold to visit. But this is an understanding that we still have a population increase, but we're also seeing new systems that are actually supporting individuals in healthcare, in building controls, things that actually improve, hopefully, our lives. So this is the whole plethora of Internet of Things. Okay? What we've been focusing on for information security historically has only been the pink area. Okay? We've kind of not done any of this, and a lot of these are systems. Matter of fact, I just did an assessment against a logistics company, not patched for 12 years, running out of date this, no passwords, RF was open, blah, 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 blah. Okay? And this, the company actually designs and builds this, replicates this every month someplace in the country. So, crazy. So there's an opportunity from a security standpoint to look at all this. Okay, internet, the historic internet growth. If you notice, 1970, there was actually a day where everybody had to go from the old protocol, turn their computers off, and reboot them with the new software and go to IPv4. Guess what? We couldn't do that with IPv6. Something about 6 billion computers, we just can't upload and patch them all at the same time if anybody would actually allow us to patch them, okay? So we saw growth, but during that growth, because we started seeing extreme growth, we had to define a whole bunch of new protocols and changes. We had to add NAT. NAT is bad. It really is not a security product. We'd have RFC 1918 to support NAT. We had to have classless, classful classless, yes. CIDR blocks, DHCP, and then we had to actually add, it was funny, at one point web servers only ran on a single IP address. And after the study from IETF, Internet Engineering Task Force, who writes the protocols for the Internet, once they made their announcement in 1993, we started redesigning Apache, which, by the way, you know what Apache stood for? It was a patch-y configuration of the NCSA open source code. So that's where Apache came from, if you didn't know that, which I think is funny. So we helped design it to create virtual servers, because at one point, one server per IP address. Now with web services, we have many devices using other techniques on one IP address, which, by the way, adds confusion and makes it harder for us for security. And that I actually have an hour presentation on, but don't have the time to talk about that. So this is today's security environment. Okay, these are like, let's see, NATs, yeah, okay, and bridges and gateways. And, you know, this is the commons because it's all dirty and everything. So security wasn't built into IPv4. And by the way, the address assignment based on Vint Cerf, the father of the internet, he said, well, you know, we're going to use a 32-bit number. And the world's only going to need, because there's less than 200 countries, let's say we're going to have 200 countries. And each country is going to have a network for their governments and a network for the commercial side. Awesome. Now we know how big of an address space we had, and that's how the IPv4 infrastructure was actually scoped. Okay? And because of that, a lot of changes had to take place that at one point caused routers to have problems and things like that. So we've been working since '94 to extend the life of IPv4 until we could come up with some kind of replacement. Sadly, a lot of the aging infrastructure still sits out there. I found a router that's 15 years old last week when I was looking at it that had a very, very, very old version of an operating system on it. Very bad. We've also lost our end-to-end trust because we have NATs and CDNs, and we have all these other middle box technologies. Each of those middle boxes actually take us one level away from being able to trust a specific machine or a specific individual. In the early IPv4, we had a book, which you basically open up and go, I need to go find this. Here's the data that's here, and here's the IP address, and here's the administrator. Awesome. Okay, it was a text file that we would print, but, you know. The other problem we have is negative externalities. People are unwilling to fix their infrastructures if it doesn't help them directly. They directly will not provide a certificate on their system unless they can see personal benefit, not benefit to their customers. They won't support DNSSEC because, well, it's going to cost them time and effort. Therefore, if anybody gets, you know, redirected to somebody else's system, servers, VPNs, not a big deal. Same thing with proxy, same thing with a lot of technology. So basically, we have this mess on our hands with IPv4. We have a chance to change things, okay? This is the war we're in. Yeah. They're coming from all directions, and we're all standing in line. We have to be close because there's so few IPv4 addresses. So let's talk about how fast we can scan. 6 minutes, the whole internet. Do you feel comfortable now? Okay, so if you put a system on the internet, in the next 6 minutes, somebody will scan you. Actually, multiple people will scan you. Which means, see that speed for discovery? Yeah. Microseconds. Compromises on systems that have been detected for a specific thing are about 2 minutes. This is a study I did 4 years ago. Makes me feel really comfortable and warm and fuzzy plugging anything into the IPv4 infrastructure. The impact of cybercrime on the industry, on the world today is 2017 was about $450 billion. And a single attack, and I was talking to the group yesterday, was that businesses are either hobbled, sold, or die within 10 years after a major compromise. And we discussed specific companies that in the last 5 years have been found to be compromised and then were sold off for pennies on the dollar. Okay? Or going out of business. Or closed 3/4 of their stores. Or whatever. Governments, if a government is hacked, we lose their data, that reduces our trust, right? And lastly, we have lifelong burdens when our identities are stolen, so that's a real problem. So, yes, you are here. Yeah, that right there. So, for IPv6, everybody's saying, nobody uses IPv6. Okay, in the world, and this date right here is interesting. The 2012 is World Internet Day. This is when we actually turned it on. Before this is when crazy people like me spent our time watching packets move back and forth and doing both fun and evil things to it. Okay? Starting June 6, that funny, 6/6, anyway, 2012, we started seeing growth. If you noticed, the world is already at almost 21% as of today. And everybody says, but what about the US? What do you think? Could we call that 40%? That's pretty significant. So how many of you are securing your IPv6 infrastructures? 100% of your technology supports IPv6, at least your host-based systems and your servers, but not so much your security products. And we won't go into detail about that, but it's a little bit disconcerting. So you have one of two choices. By the way, I love this picture. This just makes me laugh. So comparison. Deployed in 1970, where we actually turned all the stuff off and returned it back on. It was experimental for IPv6 since 96, and actually gave a presentation in 96 about IPv6, which is pretty funny. Maximum devices are 2.4 times 10 to the, well, I didn't put that up there, that's funny. The term is 240 undecillion. So for your interest, you can look that up. It was commercialized in 1990. IPv6 went world on 2012. You may not be aware of this, but last year, the Internet Engineering Task Force has made a commitment not to make any changes to any protocol that runs across IPv4 only. That's a risk to anybody running only IPv4. Okay, so if they find a major flaw in something, they can patch it, but it won't become a standard to ensure that we have consistency of communications. So that's an interesting thing. The other thing is there's already an end of life chosen. This is the initial. 2022. Wow, we're going to be really busy upgrading stuff, aren't we? And yes, this makes me laugh. One year at major conference, I security conference, I put together a bunch of these and printed them, and I tested almost 200 companies that supposedly supported IPv6, and everyone except for 4 received my sticker of support, which is fun. The other ones received that one. Current estimated shelf life of IPv6 and underlying protocol is 2060 to 2100. So, and that's all depending on a bunch of other things. There's technology for the galactic internet and planetary internet right now. There's protocols for that. It's pretty interesting stuff. So you need a unique addresses to connect devices. You really do. Sir? Yes. Yeah, you can go to the NIST standard. There's a NIST standard for testing IPv6 products. I went around, made sure the interfaces worked, I made sure the administration worked, and I made sure that if I gave it a few packets, it could detect it, and within 10 minutes, I could find a product actually failed. So it was pretty interesting. So anyway, so this came out from Ken Gear. If you haven't seen him, he's a great presenter. I'm very impressed with the man as far as presentation skills. Someday I'll be that good. He basically did, while he was at in a research position, he did an analysis against how do we fix cybercrime and cyber threats. So he approached it from the technical. He approached it from the military, the political military, which we keep on hearing people talk about it, and the political technical. Things like, let's create cyber deterrence. We keep on hearing that. We have a cyber arms race. We use Art of War for Sun Tzu. Please go out and pull this paper and read it. It's fascinating based on both game theory and his particular process to show what's going to work, what's not going to work, and some of these things are going to work or that aren't going to work are going to actually end up making the internet and operations using the internet even worse. So just want to mention that, but he actually had a call out based on 2 years worth of studying on this, that IPv6 with good crypto provides end-to-end trust. Therefore, there's a better way of providing a more trusted infrastructure. So you guys have heard of the kill chain? No kill chains here. This is the survivability model for resilience. I want to mention this because I'm spending a lot of time, if you see other presentations I've given over the last year, I'm working on a survivability model called anti-fragile. But I'm trying to put this in context to the discussion we're going to have on IPv6. The closer to this side that we can catch an attacker, the least expensive it is on the organization. The further we get to here, this is where the boom starts. This is where the big money starts for a lot of people. And that's why a lot of organizations are focused on trying to fix this. But if you can get ahead of the game, it's very good. The other side is that Win Shortall, who wrote a book called Time-Based Security, discusses from an analog standpoint that we have to basically have protection has to be greater than the ability for us to detect and respond. Today, most of our technologies assume that we can detect and respond. Think about your device that's gathering your logs. How fast does it go from the sensor to the SIM, and somebody either automatically or gets in the way to do a response to be able to fix that problem? That could be seconds, minutes, or hours, or days, or weeks, or months, right? Maybe years, depending on the company you're at. So the faster we can respond here, the more secure we have. There is a new book coming out, Analog Security, which will discuss this, including a whole set of mathematical formulas to actually start defining or creating a start to defining a mathematical model of what security and assurance looks like. And I'm really excited I've been part of that project. So if we're moving to IPv6, the first thing we have to do is we really have to move. We'd love to say move to IPv6 only right away. You really can't. Every organization has things went bad real quickly, mostly because you have a lot of hidden IPv4 NIS installed both in your architecture, your applications, the way we design our database, our management systems, our security systems, our SOC, our NOC, our management infrastructure, funding, everything else is focused on it. So we typically have a first step to go to Dualstack. So the first thing you have to think about is the mindset. Okay, these are only a couple. If you're interested, you can go to a website called IPv6 Bingo, and it will generate a bingo card for denial. And then if you click on the link, it'll actually give you the science and all references to all the current issues. One is that it won't have any impact on batteries. There was a study from Nokia that we can reduce our battery, or we can increase our battery life anywhere between 6 and 20-some% by going to IPv6 only and getting away from IPv4. Because for every application, I have to make a connection. I have to create a NAT, open a firewall someplace. I have to open on my side, and I have to open on their side. And then for every CDN and everything else along the way, I have to maintain state on all of that for every application I run. So your phone is running how many applications? Has to make so many connections. It actually maintains state so that you can actually communicate. So v6, data sent, there's no NAT, there's no state required, it comes back life is good, okay? Because we're trying to take state away from the network infrastructure and put it on the hosts. They're a little bit better for dealing with state. But yeah, these are fun. No business value. I want to mention this. Is anybody in data centers? Anybody do data centers? I'll mention this. LinkedIn and Facebook have said that once they move to an IPv6 only environment, they saved anywhere from 9 to 20+% operational and staffing, and now they've created new models. They've actually reduced programming costs and lots of other things. So this is a big deal. So that's just one example. So I just want to mention that there's some interesting things. The other thing is, if you're going to get people trained, don't just train your network engineers. Make sure your help desk, how are they going to answer, if they type, netstat or whatever, how are they going to represent to the customer what that means and how to troubleshoot that stuff. The defenders, if you're doing defense, you should actually have a real good handle on IPv6 because there's some really cool features, and we're going to talk about a couple of them. And your programmers have to know how to write it, because the programmers that we have today, some of them are using old libraries that don't support IPv6 and have flaws in them. One of the challenges that we have today is that because of that long build-up, because we didn't want to restart the internet, we had 4 generations of IPv6 protocols and standards. Depending on the company that you've worked with to buy products and services, even today, you could have any of those generational issues in it. The newest one actually has a lot of fixes for security and operational issues. The older ones don't. So you'll find code in products that have major flaws in it. So I want to mention that because this is what I've been trying to crusade for to get fixed for the last umpteen years. The other thing is problems exist when you migrate at layer 2 through layer 7. We found Ethernet cards that don't support IPv6. So therefore, if it runs data real fast and they offload it to the Ethernet card, if it sees IPv6, it uses the CPU. Therefore, now processing and everything else slows down. And those are the kind of little tidbits that we found. Also the management layer, because the management layer needs to know that you're trying to do something that's good for the business. Procurement. I mentioned this yesterday. Something called the SDoc. Basically a procurement document requiring organizations to buy products that have security and specific sets of compliance. If you go to NIST, IPv6, SDoc, you get all the definitions and references back to the ANSI documents without paying for the ANSI documents, so that you can learn how to use this in your procurement policy. Interesting, organizations that have used this process have improved security because every new procurement that says I have a processor in it and I have a network interface must follow this standard. Whether it's there has to be a patch, I have to be able to do real authentication, there has to be encryption, whatever it is that your standard requires, has actually saved money over time for companies that have done that. And I want to mention that because the IPv6 community started that 4 years ago, and we've had some real successes on not only IPv6 compatibility, but also security of improvement of devices over time. Okay, if we're running Dualstack, we have this crazy problem. So early in the deployment of IPv6, we thought about, wow, we're going to have oceans of IPv6 and islands of oceans of IPv4 and islands of IPv6. And we had to create all these protocols so everything talked. So we started creating lots of protocols. I didn't include them all because it would go off and it would be too small and you wouldn't be able to read it and not real useful. On the other side, now we have protocols to deal with islands of IPv4 across IPv6 oceans. Okay, so these things cause real havoc. One specific item I want to mention. So when do you think the first published vulnerability and attack using IPv6 was? Actually, the first published, because they had logging on, was 2001. Okay, that's a long time ago. Okay, if you go to some of my previous presentations over the last 12 years or whatever, 15 years, I keep a timeline of all those compromises and what caused them, what was the root cause, could they detect it, could they not detect it, things like that. So these are a real headache for us when we're in an IPv4, IPv6 environment. The other thing, these layers can be deep. We have found GRE with IPv4 with IPv6 embedded in it as ways of getting around IDSs, intrusion detection systems. Okay, so this impacts us from a security standpoint. We have to be able to detect this. And running Dualstack is expensive. So the surface area's increased, it's doubled. Yes, the tunnels are a real headache to deal with. A lot of applications and security controls are inconsistent. In a bunch of products for about 8 years, I spent a lot of time trying to make sure that the firewalls worked. And in some cases, the firewalls for IPv4 would be turned on, and it would turn off the IPv6 firewall. If I turn on the IPv6 firewall, the IPv4 firewall. And some of those were commercial products. Some of those were consumer products. So you have to look at the security, the application security for anything that comes across your network. Also, the increasing complexity of DNS, because now, if I'm doing passive DNS monitoring, I can have a DNS go through TCP or UDP across IPv4 or IPv6 looking for A or quad A records. See any complexity or concern here? How are you going to monitor that and associate it with each request to see if it's a CNC or not a tunnel? Okay, this makes it rather complex. Also, budget, which is really the largest risk. IPv6, when you're running IPv4 and IPv6 together, operationally it increases it. Some people say it increases the operational cost by a third. A lot of organizations are trying to move to IPv6 very quickly. Anybody heard of LinkedIn? They're completely internally 99% IPv6 only in their data centers and internally. Same thing with Facebook. They love it. It's reduced a lot of complexity they have, which is pretty neat. And the organizations that are using internal, we'll talk about that, are finding IPv6 is pretty cool. Okay, security analysis. I still find applications that don't log the address right. You have 128 bits, and a lot of applications go, I only do 32 bits, so I'm going to whack off the front or I'm going to whack off the back, and this is what goes to your SIM. There are certain addresses that then look at, like, and map to specific nation states that aren't really attacking us via IPv6, so that's a concern. The other thing is a lot of storage and analytics engines haven't upgraded their back end, so they're representing the IPv6 address as a string. How fast is it? How fast is a binary compare to a string? Very fast. A lot of products haven't upgraded that. Therefore, if you're doing threat intelligence, you're doing SOC work, you're trying to look for some address that matches something or close to it, this has become a real problem in SOCs. Also, mapping IPv4 to IPv6. If I'm being attacked by an IPv4 person and an IPv6 person, are they the same or are they different? Shouldn't you know that? That's some of the complexity that we have today in a dual stack environment. So, end goal, yes, IPv6, and increase the pain. Make them cry. Make them painful. Make them have to work harder. Okay, so I mentioned 5 items that we can use to make it painful. I don't have the time to go into every one because the complexity of it and the time would basically be until tomorrow or the next day, depending on how much detail you want. So I'm just going to go over 5 very quickly, and I'm going to tell you why these are important. Okay? First, deny topology enumeration. When somebody does a trace route, and depending on the trace route tool, I can only define the routers, but I can check for firewalls, I can check for IPSs, load balancers, and other hidden networks, depending on which version of trace route I use. So that gives them context on which networks to go after, what's available on the network. In some cases, somebody will have a firewall which they can trace route to and trace route through. So they actually say, oh, this is the firewall. Okay, I know where that is. And oh, by the way, now that I do a reverse lookup on it, I know it's a Cisco, or I know it's a Juniper, or I know it's a whatever box it is. So this basically bleeds so much information. Information. And yes, I think that's a funny picture with the kid here and the ones hiding in the stack. So how do we implement that? In IPv6, we have a separate set of addresses. It's called a linked scoped address. It means that if I'm on the same segment, I have a unique address. You'll see this when you pull up your computers. You'll see an FE80 and some additional bits here, some additional characters here, hexadecimal. By having this, we can take this interface when we're routing from point to point and say, we're going to use, this is just an example, you wouldn't use 1 or 2, you would use a random number, a large random number. I'm gonna route from here to here. This guy would actually have that address as a default route. This guy would have that address as a default route. Now, when I'm an attacker using traceroute, I would see this. This disappears. It's at layer 2. It's now not, from a network standpoint, it looks like it's at layer 2. So I can't get a decrement. And then I would hit that. If I do the same thing here, I can again manage it. So when I do a trace route to here, all I get is that interface and that interface. Pretty neat, huh? Here's the other thing. The best choice of managing these systems would be to be out of band. Okay? The second choice is we have another special set of addresses called a unique local address. A unique local address allows you to assign some random set of bits here, and it's part of the RFC, and you can look this up, and they actually educate you on how to use this. So your internal administrators, so I'm walking around a lot, your internal administrators can have access from internal to each of the interfaces on an address that they can still connect to and do traces with. Okay? And they can apply a control here to make sure that there is no exfil of the FE, unique local addresses external. Okay? So essentially, this allows you to hide your topology and still provide management for each of these systems, which is pretty cool. Okay? And these are not global addresses, so that's nice. Let's see. Next fun thing. So, make sense? Okay? Second thing. Let me tell you a story about attackers. Attackers will choose passive, especially free services, first, and then paid-for services. And some of these paid-for services are extremely expensive, but you have to know they exist. We identified over 100 so far that we can classify on V4 that are doing scans and then selling that information, which is interesting. They can do active, but then they have a cutout, which means they have their own VPNs, they have their own proxies, they're using Tor. So they basically have a cutout network. They can do it for free, or there's paid service that have low, medium, and high anonymity, okay, for V4. So that's interesting. And then the last thing they'll always choose is the direct connection. We don't want to do that. So based on a study that we performed, we were able to classify these into the type of attacks. And then we were able to figure out where that knowledge came from. We found that inbound connections, the DNS queries, because we were running our own authoritative DNS, we were identifying that some of these people got this information from the DNS server, which is inbound services, HTTP, HTTPS, SSH, SQL. We said we had Telnet, we didn't. We said we had a bunch of other things, but we started seeing them show up over here. We also have outbound. This is an interesting one. If you make a connection at one point last year to NTP, another company that sells these products would have scanned your networks because you made a request to the public NTP. Kind of creepy, huh? Same thing with patch servers. We're seeing patch servers actually scan you back after you make a connection within a few minutes. We also have DNS servers, depending on whose DNS servers. POP and IMAP servers do the same thing. We have a whole list of these. It would be little tiny characters. Also, management servers. If you're on the cloud, how do you know somebody's not trying to hack the management server, which actually impacts you? Okay? Or are you using SSH when you're calling in, or Telnet to manage the server? Okay, it's on the same address as these. The attacker can get context for free or for pay. We also have search engines. Search engines are running things all the time, or they claim to be search engines. These guys are providing information out. So I'm an attacker. I have this choice. And, oh, yeah, and monitoring. How do you monitor your system? Do you ping it? Do you do a query against the system remotely? Do you log into the system and have you send logs? I mean, those are all things you have to ask a question. These also provide indication. We put up a server one place, and we kept on transmitting data. And these two, except for regular scanning, this other system wasn't known. And we only allowed a certain type of connection. We provided some false information. We found that the connection between here and here, somebody was listening on a tap and then started scanning our monitoring system too. Okay, that's the reality of today. So they can choose to do this. The process is I scan this small address space in 6 minutes. I can do a DNS lookup for it, which then provides that IP, and I can scan for it. Or I can take this address, do a reverse lookup, get this information, get other information, and go through this loop a couple times to find everything for a company. Okay? Do you feel safe now? So, for IPv6, let's talk about the address space. Is that large enough? 19 plus 19, 19 zeros. It's a pretty large address space. When you have more bits to work with in the address space, there's ingeniously fun things you can do. Okay? To brute force that address when I'm across the router, years or tens of years or hundreds of years, depending on who you talk to. Okay? That's good. There are several techniques that I teach. There's actually several others. There's a smart one, which is pretty funny, because people put web servers on an address, and they call it a :80, and it doesn't like hide anything, right? Or they call it dead beef, or they call it something that they can remember easily, because they don't want to put something in the DNS server that they have access to, or their internal DNS server. So that's pretty fun. The other thing is we're seeing brute force of DNS. Do you run your own DNS? You know somebody's not doing a DNS brute force against you? Do you get reports from your DNS provider, your authoritative DNS server provider? Anybody? Anybody? Bueller? And also reverse DNS. Your address space, the address space that your internet service provider or cloud provider or service provider provides you, is that being enumerated? Okay. V4, these are all done and everybody ignores them. For V6, these are strong indicators that somebody's interested in either something on your network or they're going after your domain. Okay. The more interesting part is they have to scan from here to here in this large field, and I have one nugget of gold in several different locations. Let me show you where they are. Okay? This confuses the heck out of people, because to get service from these things, I would have to tell you where they are. And again, that's what we do through DNS. So let's talk about how we recommend mitigating it for IPv6. Has anybody heard of a privacy address for IPv6? Okay, that's an address that will change the actual address, the last 64 bits of the address, on a regular basis. And you can schedule that on a regular basis. So as an example, say that you're going out and doing an NTP once an hour. What if you were to change it so that the address changes every half hour? That looks like 2 addresses are coming to them, right? So from a signaling standpoint, when you change the address space, you've changed your address, what happens? If they come at you, you're no longer at that address for scanning. Awesome. That's a signal that somebody's actually looking at your site. Same thing with DNS, POP, IMAP, patching, anything that's actually outbound. Service monitoring and performance. Guess what? IPv6 allows us to take a single system and put, depending on the operating system, up to 1,024 addresses. Let's have fun with that. Why? Because the attacker today assumes that all services are on the same address. So if I have 65 535 ports times that to find a single active device on that network, how probable is it? Highly improbable? Yeah, this actually changes the game. So as an example, I can change the IP address from the allow the temporary address to exist and throttle through. I can create a static address just for monitoring, so I can check for updates. I can have another one for managing SSH. Isn't that what people do? Is they scan something, they see a web server, and they scan for SSH to see if they can brute force it. Ha ha! Now you don't have to ever put SSH on a high port. Wow, search engines. With DNS, we could direct it to a specific IP address to see if it truly is the search engine from Google or whatever. Interesting. How about HTTP? We can have a load balancer rebalancing it to that. How about HTTPS? We can have it on a different address. How about my SQL server that we don't want anybody to enumerate? And if we see somebody enumerating, that's a high indication that something either was leaked or somebody's after your organization. Pretty cool? By the way, this works real well. I have servers that have been up for 4 years, and except for the outbound initiation on the privacy address, which I get pinged all the time, just letting it do patches and things like that, I get no scanning on this. Okay, so from the attacker's view, they're looking for the little gold. They're in the wrong place. It's pretty cool. So because we have the non-allocation of space, we can actually detect, once we track that, we can detect when I made that connection, outbound, and associate it with the IP address to figure out who I was communicating with, to identify who's actually scanning me. I mean, does that make sense? It's really simple. We now have new options because of it. And by the way, we do see bots from time to time trying to find something in here. But again, that gives us early indication that there's a bot running around. We have different options that we can then make. We can block the IP, block the CIDR block for them. We can block the packet based on how the packet's formed, or we can entice them into a honeypot. Okay? So again, we have new strategies to identify bad actors and bots. Yeah. Yes, that's why we're using a special set of packet identifiers and CIDR blocks. And a combination of two are allowing us to identify specific actors. And that's been really fun. Thank you, guys. You're making it interesting. Okay, something else. Everybody like malware? You like the CNCs? Aren't they fun? Okay, well, so it's been a while since I moved a specific well-known client to an IPv6 only environment that was getting attacked all the time by different nation states. Some of the things that we learned is that on an IPv6 only, IPv4 is an indication of a CNC or bad application implemented, or a plugin that's flawed, or actually a WebRTC socket that's misconfigured, but that's another issue. This is a really strong indicator very quickly. How fast can I see this? Well, as soon as I see it go to my black hole, my DNS black hole, and I see a DNS, and I'm looking at those logs, I can make a determination based on the IP address of internally, oh my God, it doesn't like me anymore. There we just turned it on. So I'll tell you the stories this way. So very quickly, if you're monitoring the DNS service from a logging standpoint, if you see a quad A, or if you see a record query or any type of IPv4 query, you very quickly can determine that somebody either has put malware on there, they're doing CNC, they're trying to do lateral movement or whatever. This has solved the whole class of problem for most of the people trying to mitigate heavy attack. Oh, and why is this? What do the attackers embed? They primarily embed an IPv4 address, or they do a DNS query across IPv4 to find the CNC. That make sense? This has been very, very successful with a bunch of my clients that we've moved for certain areas, specifically to IPv4. Oh, by the way, those have actually, go ahead, IPv6. We turn it off. What we do is we go through and we do an assessment against that particular area, that particular group of networks. We turn all the services off. We identify anything that's IPv4. We turn it off. We update it. There's several other things we can do. We can do code audits and stuff like that for it. There's some tools for that are quick. So we can actually have it fixed if it's an internal. If it's an external, we can make recommendations for updating. But once you have that, it's a v6 clean environment. Any v4 shows tarnishment. As an example, say that they're being phished. They're pulling IPv6 only traffic from the mail server. So if they're being phished, we're going to see only an IPv4 connection. Okay, that's typical. They'll turn on the IPv6. Oh, by the way, we do leave IPv4 on purpose, just to detect this. We don't turn it off on the interface. And the reason we do that is because people use some of those IPv4 to IPv6 transition techniques like Teredo. Some of them will embed that code in their malware, and that also gives us a strong indication. So these are all just indicators we've been able to find very successful and very quickly. Detection is a few milliseconds for the log to process and for it to be shoved into something to detect it, which is pretty fun. Is that pretty cool? Okay, black cat. Find the black cat. When you're setting up a new device on the internet today, how many people set up a new device and you get hammered and then all of a sudden you find that the system is compromised? I'm so tired of that. So what you do is, has anybody heard of DNS RPZs? Think about it like it shares information based on the IP addresses that you allow it to share with. So if your internal addresses are A and the rest of the world is B through Z and lots of other characters, you can create a firewall that only allows when a source address within your organization makes a request. This could even be just the engineering group. Makes a request, they're the only ones that can do the DNS query. Okay, that's pretty cool. What that does, that provides logging where the source is, the destination, and it also gives you indicators that if you see that any of this information has been leaked, besides from these source addresses, you very quickly can identify some kind of compromise or some kind of leak. Okay, that's pretty cool. So basically you base it on the source of who's making the DNS query. So you can block certain countries, certain organizations, things like that. In v6, we have the ability to block whole continents. Okay, pretty cool. Because there's a specific network block assigned to different continents. So if I have internal but not external, all that stuff we talked about, enumeration, discovery, gets kicked into play again. This works really well. Again, I have servers that have been up for years, 4 years. I have really good time to see if anybody looks at them. Nobody's scanning them. It's awesome. Would you agree that these all increase the cost to the attacker? Okay, yeah, pretty quantifiably. So yes, this is what pays for my hotel room. This is what we do basically in threat intelligence, indicators of compromise, custom IDS, and other weird things if you're interested. And then we do a bunch of services for readiness, assessment, testing, security testing, SOC integration, and attack and defense. And that's all I'll mention about that slide. Okay. Do you have any questions? Did that make sense? I try to make it as simple as possible to roll the different features. Like I said, there's lots of other features that are a little bit more complex, require some coding, things like that. Things like moving networks for DDoS protection, where we can integrate a signal that all the addresses on all your servers change addresses to a different address block. So they're basically DDoSing you here, but now you're here. DNS lookup. It's a DNS lookup. All the bots don't do DNS lookups. They use IP addresses. The ones that do DNS, they usually pull it back once, or you can actually identify the bot doing that type of DNS query. So, but that's one of the fun things. So, any questions, comments? Did you get enough swag? Okay. Have a great day.